Hi. I came to MIT in the early. I'm sorry. You hear me? No. No.
This is a microphone for recording. It doesn't amplify. You just have to speak more loudly.
Well, I'm sorry. I have a hard time speaking really loud, so I hope you hear me. I came to MIT. I got a scholarship from France, and Jean-Louis Lemuel and Claude Allègre helped me to get here. And so, in fact, I was connected to Ted Madden even before I knew him, and even before I showed up at MIT. And I came to work with Bill Brace and Joe Walsh on the transport properties of rocks. When I came, I knew absolutely nothing about networks. But very soon, I learned networks and how they can be used in many, many different ways to model rocks. And in fact, I love networks. I continue to work with them all the time. What I want to show you is the problem of the connectivity of the poor network in rocks. And I think this has been mentioned already. When you have a rock that is pretty dense, then you introduce microcracks, maybe by squeezing the rock. Then they eventually connect, and then the transport property change drastically. And so this is pretty much known as a percolation transition. What is, so you see that the permeability here is changing very fast as porosity is not changing very fast, and that is due to the connectivity of the cracks. So this is very sharp. I think it can be understood well with percolation theory. This is different. Here we have Fontainebleau sandstone, and this is a rock that is undergoing chemical diagenesis. Joanne Frederick measured the size of the pores as a function of porosity and permeability, and so I give the numbers here to give you an idea. They don't change, really. There is a very little change in the size, in the mean size of the pores, in the hydraulic radius as you go, and you see that permeability is changing immensely. It's even changing pretty quickly here as a function of porosity. So what is happening is that connectivity of the pore space is changing as well. And I think this is a very important effect. So I tried, I need to go back to explain a few things about network, how to use networks and percolation theory. So this is just to show that if you have a network and you remove or you add branches, then there is a transition from connection to disconnection. The other parameter is the probability to have a branch or not have a branch, and it's called P. So when P is below some threshold value, then there is no connection. When it is above that percolation critical value, then we have a connected network. In between, the property of a network which is just at the percolation threshold is very complex. It's a fractal, and so you have patches of connection and patches of disconnected at all scales. It's correlation length diverges in this region. The people who work on, physicists who work on percolation theory, they like to talk about universality. What that means for me is very simple. If you have a property that in the network that is independent on the type of network that you're using, let's say simple cubic, BCC, FCC, if the property is valid on all types, then it is universal. If it's only valid for one type but not the other ones, then it's not universal. So when a property is not universal, then it's very difficult to imagine that it could be applied to rocks, right? If it is universal, we are not sure that it can be applied to rocks, but at least it has a chance. So it's very important to test this. This threshold is not universal. So with different, you see simple cubic is 0.25, BCC 0.18, FCC is the most connected, it has 0.12. You have to remove lots of branches before you can disconnect this network. And what is universal is the behavior of certain properties of the network when you reach this limit. So if I call G the electrical conductance, imagining that these things are small resistors put together, then it is proven that the conductance of the network is a parallel function of this quantity, P minus PC, the distance you are from the percolation threshold, from above, of course, not from below. And the exponent of the power law is valid for any types of networks. So it is a universal, it has a single value that is true for SC, BCC, FCC. And in fact, it has been generalized to continuous percolation and things like that. But the problem with rocks, especially sedimentary rocks like Fontainebleau sandstone, is that P has no sense. We don't know how to define the probability to have a pore or not to have a pore in a certain place. So I wanted to try to find something that would replace this. And coordination number is a very interesting thing. It's the number of branches per node in your system. So this can be, it's difficult, but it can be defined in a rock. Certainly, it's very easy to define in a network. And what I want to show here is there is a very clear linear relationship between the coordination number and this probability of occupancy that is used in percolation theory. The other thing which is very nice is that the percolation threshold for the coordination number is actually universal. So Z at disconnection is equal to 1.5, or should be close to 1.5 in 3D. In 2D it would be 2, but you know, rocks are 3D, so we are using this. So you see here we have 1.5 for FCC, BCC, SC. And it is, instead of using P as an order parameter, maybe we can use Z as an order parameter. And so I tried to do simulations on networks, measure permeability of the network or measure the electrical conductivity of a network as a function of Z. So I took FCC, BCC, SC networks and removed them to change the coordination number. And I also distributed the pipes, the radius of the pipes, with different distributions. So this is the normalized standard deviation of those distributions. So you see black is a nearly homogeneous type of network, homogeneous network. 0.3 a little bit more heterogeneous, 0.55, 0.8, etc. 0.05 is way too small for rocks. 105 is way too big for rocks. Rocks tend to be in between 0.3 to 0.8, something like this. That's the standard deviation normalized to the mean size, right? And I used also distributions of the log of R instead of distribution of R, because it is, I think, observed in microstructure of rocks that you have a lot more small elements than big ones. So a log uniform distribution is more appropriate than a uniform distribution, or log normal more appropriate than the normal distribution. Anyway, what I get is power laws that are universal in a sense that the data points here are mixing of FCC, BCC, and SC. So there is no effect of the type of network that I was using, and I get these power laws. They are very well defined. And so this one is the inverse of the formation factor as a function of z minus zc, z minus 1.5. Here it's permeability as a function of 1 over f, the formation factor, and in a log-log. So power law would look like a straight line. So now if I use this, I can shuffle, do a little bit of algebra, and then I can get to these expressions which can be used as a model of permeability and a model of inverse formation factor. So permeability, this Ck is a constant which depends on the heterogeneity level. So this is a function of sigma. R is the hydraulic radius of the rock. L, the length, the pore length. Z minus dc is the coordination number minus the coordination number 1.5. And beta, the exponent, also depends on the level of heterogeneity. So these two equations describe two transport properties. I can mix them together and then get this, where the z, the coordination number, has disappeared. This is interesting to do because, in fact, there is almost no measurements of coordination number in rocks. Now that we have 3D imaging, at a very precise 3D imaging, it can be done. It is unfortunately very difficult. I will just give a little bit of the background on the difficulty to measure the coordination number in 3D images. So anyway, this is nice because you don't have, all you need to have here is the pore length, the pore radius, formation factor and permeability. And if I go to completely homogeneous system, then I will find, alpha becomes equal to 1, and then you get this, which is the famous Patterson and Walsh and Brace expression that was published in the 1980s. Okay, I tried to test this model. Very difficult to test because you need to know so much about the rock. It's very rare, really, to have all these things measured at once. In fact, I think I know only Fontainebleau sandstone, and the Z is quite doubtful, in fact. There's difficulties to be sure that what was measured was really equal to Z. In unconsolidated sands and glass beads, Z equal to 6, so we can test them, and I just show you that it seems to work. I just want to point out that I could have put these dots exactly on the 1-1 line. That's not a problem. I just change a little bit something. But here, I got this result because I tried to fit the 3 together. So now, if you manage to, for this one, you bring this thing exactly on the line, then it's not for the other ones. So this is the best compromise to fit the 3 equations at once. Now, I would like to, this is the new, something that Chinese students with whom I work, they are in Southwest Petroleum University in Chengdu, and they have this idea that you can change the connectivity of not of the pore space, but of the conductive pore space, the pore space that is filled with brine. And brine is electrically conductive, whereas oil is not. So you can change the connectivity of the brine saturated pore space, and that gives us a way to see how a change in connectivity is accompanied by a change in electrical resistivity, and we can test my model. So I put this is from Lenormand. He worked in the 80s and 90s on invasion percolation and bond percolation. And here you see, this is a physical network etched in a glass plate. And then you can see the non-wetting phase white penetrating into the more dark wetting phase. So this is drainage. And the difference between the two is that in drainage, pores are invaded from the largest one to the smallest one in declining order. But there is a condition. The pore must be connected to the non-wetting phase in order to be invaded. So for example, a very large pore here cannot be invaded now because it's not in contact with these dendrites. But eventually there will be, and then the process continues. In imbibition, water makes a film along the pore walls, and so you can have flow along the pore walls, you can have flow in the water film. So you see here, white is still the non-wetting phase, and here we have something that looks like an island of wetting fluid, but in fact it is not disconnected from the rest of the wetting fluid because there is this film along the bottom of those conduits. So that's why this corresponds to a different percolation process. And so these Professor Lee and his student Tang, they did these network simulations, and you see how the percolation the coordination number of the wetting phase is changing as a function of saturation. So it goes from 6. This is done on a simple cubic network. So you see how it decreases with the saturation becoming smaller. That's invasion percolation, bone percolation. They are not too different, but there is a difference. And then the other parameters can be measured too. The average pore size, the average, you are changing also the heterogeneity level when you do the invasion, because the large pores are invaded, so you are left with a different distribution of pores. And so, when we put all this into my model, this is what we get. So the comparison here is the dots are calculations on the networks, and the lines are the model. So with bone percolation, it works pretty well, I think. In invasion percolation, it works okay. There is a problem for the red one, meaning the most heterogeneous. And that's where we are at this moment. This can be transformed into a model for the resistivity index as a function of saturation. And I think they are working at this moment trying to test that model with experiments. Okay, coordination number is not a topological constant. I have to stop?
Well,
okay.
Couple minutes.
Okay, so I just want to point this out so we know that coordination number is a pretty tricky thing to measure. It would be easier if it was a topological constant, but it is not. The topological constant is the Betti number. It's the number of branches minus the number of nodes plus 1. And you can see that these three examples, they are the same Betti number, so they are completely equivalent from the topological point of view, but the coordination number is not the same. So my point is the coordination number must reflect the transport property. And that goes with the philosophy of the network modeling, where dissipation of energy, the resistance to flow, if you want, is all into the branches. The nodes are only used to calculate, to apply conservation of mass or conservation of charge or something. So if a branch like this has a resistance that is very small, if there is almost no dissipation of energy in it, then this applies. We are just as well to use this model to make it a big node. If it is not negligible, then we have to use this. So the point I'm trying to make is that coordination number is not a simple geometrical property. It depends on the transport that we are trying to model. And there was a nice study by Dorian in 1988. He tried to make measurements of coordination number from 2D sections. When you think that the coordination number is a 3D property, so he used very interesting tricks, and he got some pretty nice results that seem to give a very good fit with data on Fontainebleau sandstone. And conclusions. I think this is the thing that I learned from TED. There is no end. So I don't have, my conclusion this year will not be my conclusion in 10 years. And so thank you.